Hello everybody, in this video we're going to continue with Chapter 3, Sequences and Series, specifically 3.3, Geometric Sequences. So what would be an example of a geometric sequence? Let's start with, say, number 3, then the next term 6, 12, 24, 48, 96, etc. So this is a typical geometric sequence. Notice that we multiply by 2 to get the following term of the sequence, and this is what's called a common ratio R. Recursively, we can see that the nth term is equal to the previous term times the ratio. But what would be a non-recursive formula? Well, for these formulas, we would have to take the first term. So let's say 3. So notice that we get 6 by multiplying by 2, and then we multiply again by 2 to get 12, and then by 2 to get 24, and then by 2 to get 48, by 2 to get 96, etc. So what would be the pattern? Notice that since the sequence is 3, 6, 12, 24, 48, 96, etc., the first term would be 3 times 2 to the 0, then 3 times 2, then 3 times 2 to the 2, 3 times 2 to the 3, 3 times 2 to the 4, 3 times 2 to the 5. So notice that this is the first term, this is the second term, this is the third term, fourth term, fifth term, sixth term, and so forth. So what would the general formula be? Well, notice that the nth term would equal the first term times the common ratio to the power of the index of the term minus 1. Notice that 0 is 1 minus 1, 1 is 2 minus 1, 2 is 3 minus 1, etc. So this would be the general formula for a geometric sequence, and this one would be a recursive formula for any geometric sequence. So next we have example 3.9, and it says for part A, find the geometric sequence with the first term 2 and a common ratio 3. So when they say find the geometric sequence, it means just write the sequence. So this would be 2 would be the first term, 6, 18, 54, etc., right? That would be the sequence. And if they want a general term or to describe the sequence, we would say that the nth term is equal to 2 times 3 to the n minus 1. For B, it says describe the sequence. So it starts with 3, then negative 12, then 48, then negative 192, etc., right? So this obviously has a common ratio of negative 4. So the common ratio is negative 4, and we know that the first term is 3. Therefore, the nth term is simply going to be 3 times negative 4 to the power of n minus 1. Now notice that when the common ratio is negative, the terms of the sequence alternate in sign. For C, they ask us to describe a sequence which is 1, 1/2, 1/4, 1/8, etc. So here it's obvious that the common ratio is 1/2. The first term is 1. So the sequence would be, the nth term would be first term, which is 1, which we won't write, and then 1/2 to the power of n minus 1. For part D, they want us to graph the sequence a sub n is equal to 1/4 times 3 to the n minus 1. Now this, if we do it graphically, we should do it as a function, right? So we'd say that y is equal to 1/4 times 3 to the x minus 1. So this graph is obviously going to be exponential. We're going to take a look at it. So here we are with the GDC, and we're plugging it in as y equals 0.25 or 1/4 times 3 to the power of x minus 1. So we hit the graph button, and there you go. You get an exponential function. So these geometric sequences can be modeled using exponential functions. So next we have example 3.10, and it says, find the 10th term of a geometric sequence 2, 4, 8, 16, etc. So the geometric sequence is 2, 4, 8, 16, etc., right, as I just said. Now this tells us that the common ratio for this geometric sequence is 2. Notice that 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So this is our common ratio. And we also have the first term. The first term is 2. So we have everything necessary to find the nth term, because the formula for the nth term of a geometric sequence is going to be the first term times the ratio to the power of the index of the term minus 1. So if you want to find the 10th term, it's going to be 2 times 2 to the power of 9. And this is going to equal, if we plug it into the calculator, it's going to be 1,024. Next, we have example 3.11, and it says, at 8 a.m., 1,000 milligrams of medicine is given to a patient. At the end of each hour, the amount of medicine in the patient's bloodstream is 60% of the amount present at the beginning of the hour. A. What portion of the medicine remains in the patient's bloodstream at 12 noon if no additional medication has been given? So this is obviously a geometric sequence, and the first term is going to be 1,000, the initial amount of medicine, and the common ratio is 60%, so this is going to be 0.6. Therefore, the amount of medicine present in his bloodstream would be equal to 1,000 times 0.6 to the power of n minus 1, where n is the time in hours. So here you have to be careful with the time, because the first dose is at 8, then it starts gradually going down. So 9, 10, 11, and 12. So 12 is the 5th term of the sequence. Therefore, at noon, we would say that it's 1,000 times 0.6 to the power of 5 minus 1, or 4. And then just plug this into the calculator, and you're going to get 129.6 milligrams. For part B, it says, if a second dose of 1,000 milligrams is given at 10 a.m., what is the total amount of medication in the patient's bloodstream at 12 noon? So we know that at 12 noon, he's going to have this left after his first dose. But then if he's given another dose at 10 a.m. Of 1,000 milligrams, and we know that 10, 11, 12. So this would be the third term of that sequence. So that means that we would have to add an additional, this would be 1,000 times 0.6 to the power of 2 in this case, 3 minus 1. So this to the power of 2, and that's going to be an additional 360 milligrams. 360, but we have to add what we knew from before he would still have remaining in his bloodstream at noon. So this would be plus 129.6, and we're going to get that the answer for B is 489.6 milligrams. In the next slide, you're going to find some notes about compound interest. Compound interest is an example of a geometric sequence, and we're going to see that through this table here. A sub 0, or the first term, is equal to P, the principal or initial amount. R is the annual interest rate. R is a percentage, so it's written in decimals. T is the number of years. So notice that when you make a deposit, let's suppose you're putting money in the bank and they're giving you annual interest. So at time 0, you deposit the principal. After 1 year, this would be the second term, you would get the principal plus the principal times the interest rate. Or the principal times 1 plus the rate. The second year, you would get what you got the first year times 1 plus the rate, or the principal times 1 plus the rate squared, and so forth. So notice that you get a general formula where t is time, and after a certain number of years, the money you would get back would be the principal times 1 plus the rate to the power of t, t being time. Then we have the case of interest compounded n times per year. So compounded interest more than once per year has a different formula. Notice that the principal is invested, but the interest is paid n times per year. So then R over n is the interest paid every compounding period. Since every year we would have n periods for t years, we would have n times t periods. So that helps us derive the formula for the amount as equal to the principal times 1 plus r divided by n to the power of n times t. We continue with example 3.12, and it says 1,000 euros is invested in an account paying compound interest at a rate of 6% per annum. Calculate the amount of money in the account after 10 years if the compounding is A, annual. So annual compounding is simple, right? It's just going to be the initial amount, 1,000, times 1 plus the rate, which is 6%, that would be 0.06. And because it's 10 years, this would be to the power of 10. So this is going to equal, in euros, it's going to be 1,790.85. For B, it's quarterly, so it would be the same formula, but we would have to divide by n and also multiply the 10 by n. So this would be 1,000 times 1 plus 0.06 divided by 4. That means 4 times a year. And this to the power of 40, right? So this is going to equal, in euros, let's see, 1,814.02 euros. For C, it would be monthly, so that means 12 times a year. So it's the same thing again, 1,000 times 1 plus 0.06 divided by 12 to the power of 120, or 12 times 10. And this was going to give us, in euros, 1,819.40 euros. Now we'll do example 3.13. And it says, you invest 1,000 euros at 6% per annum, compounded quarterly. How long will it take for this investment to increase to 2,000 euros? So this would be then that 1,000 times 1 plus 0.06 over 4, because it's compounded quarterly, to the power of 4 times the number of years. When is this going to equal 2,000? That's the question here. So if we do a little bit of expansion here and simplification, notice that we can divide by 1,000, and then we can add this in here, and we're going to get 1.015 to the power of 4t is equal to 2. So here we would have to solve this for t. What we'll do is that we'll use the GDC, and we're going to graph y equals 2 and y equals 1.015 to the power of 4x, and we're going to find their intersection. So here we are with the GDC, and notice that we have plugged in the functions that we just mentioned, y equals 2, and the second one would be y equals 1.015 to the power of 4x. So let's graph that, and there we can see that they have an intersect. So let's just calculate that. We go to second, calculate, and then intersect, option 5, and it's going to say first curve, yes, second curve, yes, hit enter, and there it is. Time would be 11.638881. So that's about almost 12 years, so 11.63 years. And we can route it to 11.64 years, so that's the time it would take. 11.64 years. So we continue with example 3.14. Part A says, Samantha puts 15,000 euros in a bank account, earning 6% annual interest, compounded monthly. How much interest will she have earned after 20 years? So here they want to know how much interest money and after 20 years. So let's recall that for compound interest, we know that the final amount is equal to the principal times 1 plus the rate divided by the amount of times it's compounded per year to the power of n times t. So in this case, the principal is 15,000. So the final amount is going to equal 15,000 times 1 plus the rate. And it's 0, let's see, in this case, 0.06 because it's 6%, right? 0.06. And it says it's compounded monthly, so that means 12 times per year. So this divided by 12, and then to the power of 12 times 20. So we plug this into the calculator. Now you have to be careful here with all the parentheses and all that. And you're going to get 49,653.07 euros, right? That's the amount of money that she would receive after the 20 years. But they're not asking about how much money, but rather how much interest. So that means that we have to subtract the principal from this. So I would say this minus the initial 15,000 euros, 15,000. And then from here, we're going to get the answer, which is 34,653.07 euros, right? 34,653.07 euros. That's in interest after 20 years. So for part B, we have, you want to invest 1,000 euros. What interest rate is required to make this investment grow to 2,000 euros in 10 years if interest is compounded quarterly? So that means compounded 4 times a year. So we want to invest 1,000, right? So the amount is equal to 1,000 times 1 plus the rate, which we don't know, and it's what we have to find out, right? So that would be R, divided by the amount of times it will be compounded. It says quarterly, so that means every quarter, which is 4 times a year, so 4. And this to the power of 4 times 10. So the idea is, what interest rate do I need for this to reach 2,000 euros, right? So this is equal to 2,000. Okay, so how do we solve this problem? Well, I'm going to show you how to solve it manually, right? So here, notice that this is the same as saying, if I divide this side by 1,000 and I divide this other side by 1,000, I can do that, right? So I'm going to get that 1 plus the rate over 4 to the power of 40 is equal to 2. And then I can apply the 40th root to both sides of the equation. And I'm going to get that 1 plus the rate over 4 is equal to the 40th root of 2. Okay, so I'm almost there, right? Because now I know that the rate is equal to, or the rate over 4, I should say, the rate divided by 4 is equal to the 40th root of 2 minus 1. And then finally, the rate is going to be 4 times all this expression. So 4 times the 40th root of 2 minus 1. Plug this in the calculator, and it's going to give you approximately 0.0699. Approximately, you would need an interest rate of 7%. Now we can test this in the original formula. So if you go testing it here, right, to see if it works, you would say 1,000 times 1 plus 7%. Remember that it has to be in this form, 0.07 divided by 4, and this to the power of 40. If you plug that into the calculator, it's going to give you approximately 2,001.60 euros. So for population growth, we can use the same type of formulae. Let's focus on example 3.15. So the population of, I'm going to say this wrong probably, Baden in Austria grows at an annual rate of 0.35%. The population of Baden in 1981 was 23,140 people. What is the estimate of the population of Baden for 2025? So notice that this is 44 years, so T is going to be 44. So here we can say that the population, we're not talking about amounts anymore, so the population is going to be equal to 23,140 times 1 plus the rate. Now be careful here because this is 0.35%. So we have to add 2 more zeros to this to the left. So it would be 0.0035 and this to the power of 44. So we plug this into the calculator. We're going to get approximately 26,985. So that means that the population, or the estimate of the population for Baden in 2025 would be 26,985 people. So next we have example 3.16, which will be the last one on this video. And it says, a new car is bought for 28,000 euros and depreciates in value each year by 17%. So when you buy a new car or even a new machine that you install in a factory, it tends to have a value that decreases with time, okay? So it says, part A, represent the depreciation as a sequence. Okay, so here we have to be careful because we have to use the simple formula for interest, right? For compound interest. And we could say that the value in terms of N for this car is going to be equal to 28,000 times 1, but this time we won't do plus, we'll do minus, right? Because here the percentage is being lost. So this is 17%, and then this to the power of N, right? Which in this case represents the term of the sequence, which is in years, right? So we can put this in terms of years maybe to make it a little more clear. So let's just use T as time so we understand that we're talking about time. But obviously this can be simplified into 28,000 times 0.83 to the power of T. So it says for part B, how much is the car worth after 5 years? So that is simply going to be plugging in 5 here, right? So V of 5 is going to be 28,000 times 0.83 to the power of 5. So if you plug this into the calculator, you're going to get 11,029 euros. So that means that after 5 years, the car depreciates from 28,000 euros to 11,029 euros. Part C says, assuming the car is maintained properly, after how many years will it be worth 9,000 euros? So in other words, they're saying this, 28,000 times 0.83 to the power of T is equal to 9,000. So when is this going to happen, right? We have to solve for time. So the easiest way to do this is to use the graphing display calculator. And I'm also going to use it to answer part D, which says use the graph of the sequence to display and discuss the depreciation pattern. So that's what we're going to do next. Okay, so here we are with the GDC, and the first thing we're going to do is click on y equals. So notice that when we get to that section, I have already plugged in the sequence, which is 28,000 times 0.83 to the power of x. With the graphing calculator, we do everything in terms of x. And then notice that for the second function, I have y equals 9,000, which is simply going to be a horizontal line, right? Okay, so now go to Zoom and scroll down, and you're going to find option 0 right after 9, and it says Zoom Fit. So hit Enter. And notice that we have the graphs of both the sequence and the line y equals 9,000. But I want to improve the view a little bit. So let's adjust the window according to the circumstances. So a 0 minimum for x is fine because x represents time. And a maximum of 20 is fine. That's to about 20 years. The y minimum, let's make it 0. And the maximum, they use 28,000, which makes sense because that's the maximum value of the vehicle. But let's use 30,000 just to make it a little bit nicer. And the scales are fine. So let's just hit on graph, and there we go. So notice that we can click on trace here, and this blue line represents the sequence, whereas the red horizontal line represents the value 9,000 euros. So we're going to find where they intersect. So we go second, calculate, and option 5 says intersect. Then it says first curve, the blue one, hit enter, second curve, the red one, hit enter, guess, hit enter, and there it is. So notice that the vehicle is depreciating in value. You can see that because the graph is going down, and this blue graph represents the value of the car in the y-axis, right? And the x-axis represents time. So that means that after about 6 years, so you would answer that approximately 6 years. After 6 years, the car is going to be worth 9,000 euros. And that would answer part C. For part D, we can describe the depreciation per year as decreasing with time. Notice that it's falling very quickly in the beginning, but then as time goes by, the rate at which it falls is less. So that means that depreciation is faster at the beginning, and then it slows down as time passes.